Well, good morning, everyone, and it's a pleasure to be here. It's an honour to be here. I've been working in this area now for about 20 years, so it's taken this long to kind of get the message across in that space. So it's been a while. The group is 130 people, broken up into about 40 PhD students, 40 postdocs, and 40 to 50 software mechanical engineers, depending on how it goes. It's not just in agriculture. We've been working in mining, aerospace, stevedoring, infrastructure, aviation, and a whole wide range of areas. The benefits of all that technology has been the ag and biosecurity space, because the technology gets developed and gets cheaper, and then it moves across into this area. So what I'm going to do today, though, is just focus on the areas around agriculture and biosecurity. And I thought I'd do that by kind of going through the projects in chronological order, because I wanted you to see how the technology was evolving in that space and how it moved. And it started with these aerial systems back in 1999. So we were working with drones before people knew what drones were. And we never called them drones back then. They were called unmanned aerial vehicles. And we had to build this stuff in our labs and kind of start to use it in different spaces. And I'll talk a little bit about that, how that then transitioned to on-farm robotics and away from drones now into ground robots. And then I thought I'd do I did a little bit of a lit survey in terms of what's going on in the biosecurity space in the area that we work in, to kind of see where that future is. And I'll just end with some thoughts about how we've been looking at how do you transition this type of technology into this area, and some of the kind of paradigms that we focus on. So it started in 1999, and we had some funding from various aerospace groups to look at building drones. You can see those red drones down the bottom there, and I've kind of circled the places where we had to fly them. So we had this project which ran for quite some time, over 8 years, to build drones, and these things flew at about 300 kilometres per hour, and they could carry 20-kilogram sensor payloads on there, so that's quite phenomenal for back then. But we had to build everything from scratch. So the aircraft frame had to be built at the university labs, the flight control systems, the navigation systems, but more importantly, the remote sensing systems. So we looked at radar, laser, vision, infrared technology, and what does that mean about building a map on of the environment down below. And what you see there is 3 aircraft flying within a fixed area, because what we wanted to demonstrate was cooperative decentralized data fusion. So how to so basically a network of sensors in the sky that had to fuse statistically information about what they were seeing in the ground. And they had to make decisions about where to fly next in order to improve or maximize the amount of information they were getting from what they were collecting there. But before they made a decision about where to fly next, they had to cooperate with each other. So they had to actually renegotiate their flight plans in real time as they were going through. What I wanted to point out there too was that not only did we have to build everything from scratch, but we were looking at about $700,000 per platform, right, to be able to do this. And they would fly for about 45 minutes. You couldn't fly above 150 meters within a very small area. But what you could do is, when you started to fuse this information together, is get some very accurate terrain information. So even back then, we could only use black and white cameras. You couldn't get the kind of resolution and more importantly, the frame rate. So the faster these robots move, the quicker you've got to kind of take images. So you couldn't get that with color cameras. So you could only use black and white cameras. But you could still get, when you fused the camera with the GPS and the inertial, you can kind of get the centimeter accuracy terrain maps, which are important. You can kind of fuse all that information together. But what it was collecting the data over 45 minutes, megabytes of data, but still with megabytes of data, take it home and then process that information over the next 16 to 18 hours just to be able to generate a map. So that was the kind of technology horizon that we were looking at. That went on for some while, and then if there's any benefit in military conflict, it's the fact that the technology cost reduces in that space. So what you generally have is, when there's all these things going on around the world, you get these startup companies that start to form, and then from that, they start to work on various points of technology. The technology cost starts to reduce. And it was around the 2006 mark that we could start to see that the technology was at such a cost that we could start to divert it towards applications that dealt with environmental monitoring, specifically in that space. So at this particular point in time, we could, so you'll see 2 different platforms there. The yellow fixed wing platform up the top would cost us $2,000, but just as a remote control platform. But you could start to buy autopilots off the shelf at that point in time. You still couldn't get an integrated drone. You still had to kind of integrate everything yourself together. But you started to get these platforms for about $50,000 for an autopilot. You could put it together, and all of a sudden you just put your black and white camera or your color camera underneath, and off you go from there. And this thing could fly for about an hour and a half, carrying a 5-kilogram payload. And what we did here was we also took an off-the-shelf helicopter, remote-controlled helicopter, and we just added our own sensor systems. And the same autopilot that we had in here, we could put into there, and you could start to fly this thing. And we had different projects that I'll talk about soon in that space. But really what it came down to was still systems integration. You still have to integrate everything yourself, but you're starting to see the cost of the platform come down to below $100,000 and start to do some semi-intelligent tasks. In 2007, we started to get the first machine learning algorithms working. So I come from an engineering background as opposed to a computer science background. In an engineering background, we want to kind of validate all the algorithms before we kind of put it out there. We're not just dealing with data ingestion and kind of algorithms. We wanted to show how the algorithm worked, prove that it worked, because we normally had to sign off on the system when we had to deliver it to the end user. So it was around this time that the algorithms that were coming out of the machine learning community had some sort of probabilistic basis to them that could be proved. And because of that, it was more than just a black box to us, so we can actually start to play with them. So one of the first algorithms that came out was these things called support vector machines, which were machine learning algorithms that were very simple, could only work in a kind of like, we had to deal with the world as a linear data world. But what you could do is you could take these images that you were collecting from the drones, break them up into small boxes, pull out each box, take it through these algorithms called support vector machines that you had trained before, and these algorithms would then spit out some sort of likelihood about whether something was a weed or not a weed or whatever it might be, but in a very discrete manner. But it worked, it started to work. So one of our first projects in 2007 was with Land and Water Australia, and they asked us to basically just look at aquatic weeds. Could we actually apply this system to aquatic weeds? So out the front of this, you'll see this stainless steel box that you kind of see there. It's got all the navigation algorithms on board and so forth, and the camera system. And basically we could come along and detect where the weeds were, and we could spray the weeds themselves. So it kind of looked like this, where there's a tree there and there's the alligator weed around it, and you could detect where the white is, in this particular case, where it thought the alligator weed was. It was good, it worked. It was problematic too, because at the time there were no regulations about spraying off a drone. And then you have things like downwash, because you have the rotor blades blowing, so you know how to predict where the herbicide was going was important, and that was very difficult, and we couldn't solve it back then. It was just too hard. And at the same time, it was quite interesting, because you started to get the cowboys now who thought, oh, there's a business case in here. So everyone was kind of getting drones and starting putting herbicides underneath and whatever it might be. And that's when CASA got involved and started to say, well, no, we've got to regulate this space. So it was at that time that you started to get the heavy regulation around the drone space. In 2007, we also got some funding from Meat and Livestock Australia. They wanted to see the same type of concept, but looking at woody weeds, so prickly acacia, Parkinsonia, mesquite, and how that was affecting the cattle industry. Same type of concept, fly a drone over large areas, collect all this map data. At this point, we could actually now we're starting to get into gigabytes of data that we were collecting, and we were starting to get color camera information, and it would take us about 3 to 4 hours to process, anywhere between 2 to 4 hours to process that data. So we'd have to land the aircraft, take off the data, plug it into the desktop computer, and then you could start to get some really high resolution imagery out of that. And without using any laser data, so you're just using camera data, GPS and inertial, you could start to build up topography and centimetre resolution, and about 5 to 10 centimetre depth height resolution as well. And you can kind of gave the ability to be able to zoom in and zoom out in that. And this map data, so all the little gaps that you see there was because when the drone is flying, it banks because of wind and whatever, so it misses out on information. But you could start to build up and stitch this information together. Back then, you kind of get really high resolution data, which was good for the farmer or the weed control officer or whatever it might be. For the algorithms themselves, we started to get much better machine learning algorithms. So now we start to move into, when I showed you the support vector machines back then, that were linear, Gaussian machine learning algorithms. We could start to move into Gaussian processes now at this particular point in time. So non-linear and non-Gaussian distributions, probability distributions, and applying that into the machine learning context, and to get much better resolution. So the different colours here representing different types of classification of weed species, whether they're native or plants, or whether they're Parkinsonia mesquite. But the algorithms started to get a lot better as well, and that was the trend that we were seeing at that time. We got some funding from the Australian Weed Research Council to look at wheel cacti as part of in the Flinders Ranges and trying to see that. And this was a much harder problem, because what you were seeing was the plant now was a much more vertical growth plant, so it would kind of grow in the vertical direction. So you couldn't just fly from above and look down, you had to actually fly from a oblique angle and look across. And that complicates what you want to do in terms of flight planning, because when you get CASA authority, they're going to give you authority to kind of fly over a certain area, but really what you're interested in is actually flying beyond the area and looking into that space to see where it is. And in these kinds of ranges where you've got mountains and valleys and hills and so forth, it becomes quite complex in the process. So we never actually got to properly solve this problem because the technology wasn't ready at that time. But what you really wanted was an agile drone platform with a gimbaled camera system that could point and look at any direction so that you could kind of fuse that information and bring it together. In 2011, we got some funding to try and look at whether we could detect plague. And really what this came down to was we were working with some biologists who were world experts in identifying different types of locusts, but the way they were working was they would go into a swarm, they would collect a bunch of locusts, loci, pick them up, put a little radio tag on them, put them on the ground, get a GPS coordinate. They do that for about 5 or 10 of these amongst a million. And they'd go away, they'd come back the next day and try and track down those other 5 or 10 and locate them again and try and get the GPS coordinate. The idea was that they tried to build up a motion pattern of how these locusts were moving. And because they were quite, they were experts at understanding the genetic pattern, and you could change certain gene profiles and change this pattern from, a jump and 2 hops to 2 hops and a jump or whatever it might be, and that would affect the whole swarm. And what they wanted us to do was to try and look at whether or not we could start detecting more of these locusts more continuously. So we looked at various techniques, and in this particular case what we did was you could kind of just see the little module that's sitting on top of that locust there. These are just the street signs that you see, the retroreflective tape that you've got. We just took some of those and you kind of glue them onto the back of these. And then you fly the drone over the swarm, and then you have this camera and a strobe, and you fire the strobe, so a big light, and everything, you change the camera settings so that everything goes black except for what's reflected back. So then you can start to fly over and you can start to track where these individual locusts are. So you go back and forth and you start to build up this imagery of where it's going. It gets quite complex, as you can imagine, 2 locusts coming together and they cross over. Do they kind of do that, or do they cross over in that path? So it gets quite challenging. But what you start to do is you start to build up this information profile. In 2013, again, this is when you start to get the drones, as the public likes to know them, right, start to come out, and again, the off-the-shelf systems. And what we could do at that time was actually now close the software pipeline. So now we're in a position where we actually had many different weed councils from New South Wales and in Victoria in this particular case, be able to go out there, collect data, and then give us the data, and we would just pass it through our software pipeline. And in that software pipeline, we could stitch up, collect information, build up the topography, but also pass it through the machine learning algorithms and start to detect all the different weeds that we're interested in. And we're starting to build up a database of different types of weeds that we were looking at, and more importantly, detecting things that we had never seen before that we could then pass on to an expert who would then come along and say, oh, that's that particular type of weed. But we also learnt a lot, such as the similarities between the native and the weed, the weed itself, and being able to fly at certain times of the year, especially when they were flowering. Sometimes they were giving off different spectral responses, so you needed different types of camera units to be able to detect different types of plants. And with the drones at that cost coming down, we also looked at further animal tracking. This one here, we were trying to look at endangered species, so the swift parrot. You could put a tag on these animals. We had our drone and we could fit the radio system on board, and then we could connect that into the autopilot. So going back to the very first project that I told you about, where we could adjust the flight plans, what this was doing is the drone was going up in the air and just listening to the ping signals that were coming back, and then adjusting its flight plan to try and localize where that endangered species was, so that you could send in the people that were most interested in much more readily to a certain location. So what we're seeing now was this, so now you're starting to get data fusion, machine learning, sensing, flight control all coming together in real time, compared to what we had the 13 years prior, where everything had to happen, and you'd happen over 2 days. You'd fly, then you'd collect the data, then you'd process the data, and 2 days later you'd get a report. Now we're starting to get things a lot more in real time. This is probably the biggest project that we got around biosecurity, and it was funded out of the Queensland Biosecurity Group, which was looking at the red imported fire ant and trying to detect the mounds in locations where it was was quite difficult. You couldn't fly drones because you're flying over urban areas in this particular case. So we worked with a company that was building the sensor pod and selecting what the sensors would be. They'd put them under a manned helicopter, which would then fly over the urban areas, collect the information, feed it to us, and then we'd have to go through the process. And we had to work on different ways of doing things, and one of them was, well, the solution that we found was using a thermal camera to find the hot spots. Because the fire ant mounds were of a different temperature, the ground temperature. But then you had to detect whether the mound was a mound or whether it was a barbecue or whether it was the top of a car or whatever it might be. So the thermal hotspots allowed you to shrink down to where the hotspots were. But then you used near infrared to kind of look at vegetation versus mound, and also RGB, so red, green, blue camera systems. And you had to bring all that information together under large machine learning algorithms that would then go through that process of fusing that information together. What was also interesting was to actually take the models that were describing how mounds would propagate through there, so the scientific models that were there. So when you actually bring in the data, bring in that scientific model, fuse it together, then you start to get much better results in terms of where to go through and explore in the next location. You start to couple that with satellite data. Satellite data would come in and start to give us information about where there was new urban construction, wherever there was disruption in the soil and the environment. You kind of thought, okay, that's probably where the next batch of fire ant mounds would go, and you start to do your surveillance from there. But it became a really complex software system to be able to do this now, because we are dealing with you're dealing with very, very small features in large landscapes, and the landscapes were varying. So you could train a machine learning algorithm to detect the mound on farm, but then you'd have to retrain the algorithm to detect a mound in a quarry, and then you'd have to redo it for something in an urban area. So all of a sudden, all these different background environments, you had to train the algorithms to kind of work in those different spaces. And that became quite complex as well. So now you had these overarching machine learning algorithms, detect the fire ant mound, but also before that, detect what kind of environment I was working in. And maybe I'm detecting things I don't even know what it is, so how do I bring that information together? So it became a very, very complex, this became the most complex machine learning system we had. But also, it had to be part of a more complete software system that was integrated into Queensland biosecurity, because the idea was fly, early detection, send out the information to a PDA to some person out there who would then have to go out there and check. And if there was a fire out, man, just completely destroy it, because they had to go through this. They went through a containment mode in that operation. So it was about how do you real time do surveillance, detection, and then going out there and doing some sort of containment. More importantly, if it wasn't a fire ant mound, how do you feed that information back into the machine learning algorithm so the machine learning algorithm starts to get better and better? So it was important that you not only got all the detections right, but if there were false positives, so if there are areas where you came along and you thought there was a mound but there wasn't, how does that learning come back into the system? So feeding that all together. One of the last project that we had was just finished, started in 2016, was looking at large scale mapping across the whole northern inland region, and this was about capturing satellite data, high altitude aircraft data, so like something like a fixed wing, as well as drone data that was brought in by the local council officers. And you can imagine this gets quite difficult because you've got different spectral sensors that are coming through together at different resolutions, and you have to try and calibrate all those sensors together, right, and that information together. Especially this one here, where you may go to different councils and different operators will have different types of drones and different type of camera systems. So it becomes quite complex, but you can actually start to do a whole bunch of things now, such as automated detection of weeds very quickly. The machine learning algorithms are very, very sophisticated now, so using stochastic machine learning algorithms, and all cloud-based architecture, so being able to process this a lot quicker now and being able to move with that. So that's the state of the art in terms of the kind of like the biosecurity work that we got to at this point in time. And then in about 2013, we got some interest from some. Well, actually, my interest started to peak when I was doing all this work, because you're talking to more and more farmers and how the impact of weeds in particular was impacting their bottom line. So that kind of tweaked my interest about what you could do for farmers. So how could you reduce the cost even further to help the farmers? But more importantly, trying to look at the general aspects of what happens around productivity and efficiency. One of the first projects we had was in tree crops, and I'm going to slightly touch on how we go through this process. And I don't expect you to read any of this, but one of the first things that we think about when it comes to robotics is How do you increase the amount of information? Because when you increase the amount of information, not only does it benefit the end user, but it also benefits the system itself, the automated system. More information makes better decision making. So one of the first things we start with is understanding what is the information pipeline that happens. So you speak to these growers. In this particular case, we're speaking to an apple grower and saying, okay, what do you do during the season? Yeah, okay, and as you go through there. And when we get that information, we then start to package it up. We start to break it up, around the whole season boundary. Around the whole season, what are the different tasks that they do? And again, you don't need to read through this text, but then you start to break down each one of these and say, okay, what are you actually doing there? And what I do want you to focus on is these little bracketed terms at the end of it all. What you'll see here is the first term represents how much information they have. So in this case here, they have low information about the quality, size, defects, maturity, colour, etc. of the particular plant, and that has a high impact on their decision making. So when you look around through here, anywhere where it's a high and a high, from a robotics perspective, you don't touch it because it has least return on investment to the farmer. Actually, where the most return on investment of the farmer is wherever it's low information, but it has a high impact on decision making. If you can then build a system that collects that information, increases that information to high, then that becomes the greatest return on investment. And you can see here what's important is certain aspects around counting the fruitlets, and hence a yield estimate, counting fruitlets, et cetera, being able to count all the different flowers. They become the important aspects if you can deliver that information to the farmer. So we took one of our robots and we added a large collection of sensors on board just for the fun of it. From an engineering perspective, we're just putting all these sensors on board and just saying what works and what doesn't work. It's not that this Frankenstein robot's not going to work on a farm, but what we're interested in is kind of adding all these sensors and seeing what happens. And these sensors will give you back different pieces of information, and you and I can see a tree, and we can see a tree in different spectral bands, but first thing you have to do is train a robot to understand what a tree is, and understand what a leaf is, and understand what a fruit is, and understand what a flower is. These are the same things that we do, training a kid all the way through, the same process. You start to add all this information in there. So you go through these software pipeline processes and start to go through the different aspects of training up these different algorithms to look at different aspects of a tree, so it can start to build up a model of what a tree is. And these are the same types of algorithms that we looked at before in terms of detecting weeds, just they're slightly more advanced at this point. And what happens is that if you can detect these individual features, then you can start to work on some higher order algorithms, the things that matter most to the farmer. So if I can start to detect individual flowers, individual apples, individual fruitlets, individual leaves, the stem structure, the structure, for example, the branch structure of a tree, etc., then I can start to look at higher order algorithms that are of benefit to the farmer. So one of the first areas that we worked in was in the apple industry. And this is the robot now going up and down the tree rows and doing so autonomously. One of the hard things is that you can't rely on GPS in these types of environments because your GPS gets attenuated through the tree canopy, so you can't just rely on GPS. So this thing's navigating by looking at the tree trunks and detecting where the trees are and navigating down the centre of that. And all these sensors are collecting information. The other thing I want to point out is the trellis architecture that you see here. So one of the things that we first noticed, and the things that we keep talking about with the ag guys in the ag industry, is if you start to think about what the farm of the future looks like, do you start to build robots that have to cater for every single type of farm that's out there, in which case you have to deal with unstructured and structured environments, 3D canopies, 2D canopies, whatever it might be, etc. But if you can restructure a farm, you make automation a lot easier. And these tree crops in this trellis architecture is a lot easier because all the flowers are on one side, all the fruit's on one side. I don't need to harvest or anything or look internally or estimate how many fruit are on the inside of a tree. So starting to change tree architectures, which not only optimises their manual labour process, but also allows the ease of automation to come through. So as this robot's going up and down now, you can see flowers on the left. It's counting in real time and detecting the location X, Y, and Z of each flower on each tree as it's going down the row. So now instead of a farmer making paddock-wide decisions, I think there's this many flowers, this is what I'm going to do in terms of my pollination program, what's happening now instead is that per tree we can start to understand what you need to do for each individual tree. And just before harvesting as well, you'll kind of see the apples on the left, but on the right there, the robot's detecting in real time each individual apple as it's going down there. And again, the big data process that's happening now is, oh, well, there were these many flowers there before on this tree, why am I only having this much fruit? And what does that mean about the pollination program and so forth that I need to look at? And how do I maximise my yield? In one operation, we were able to increase yield by 30%, and it was a good grower operator as well. This is just showing you how it can get a bit more complex, but if you do the right things, you can actually do it when it comes to 3D canopies. So this is an almond farm. The robot's going down and detecting each individual almond tree using the laser data and being able to segment out, I see a tree, I see a tree, I see a tree. And it's also collecting information of the soil type underneath that. When it notices a tree in the laser frame, it can pull out its vision data and it says, okay, that's where the tree is, that's where the tree is. And it then takes that vision data and passes it through its machine learning algorithm in real time again, and detecting all the different flowers and also detecting all the different almonds. And because I have laser data that tells me some sort of volume estimate of the tree, I can then start to guesstimate the yield of that individual tree. I can map out that yield on a farm, and a farmer can come along and just see what's going on per individual tree. Can even click on one that's underperforming, for example, and get the latest visual data. And it's almost like a Google Earth thing for a farmer in that process. But what you're trying to do is change that information pipeline both for the farmer as well as for the automated system as well. The vegetable industry then came on board. They got, it's kind of like getting jealous from the tree crop industry. They got a robot, so we need a robot too. But they gave us enough money to kind of think from scratch, what is it that we wanted to be able to do in a robotics perspective? Do we take a tractor, for example, and just automate a tractor? Or can we start from scratch and kind of work about what it looks like, what it means to build different types of robots? So what we looked at was, okay, we're going to go solar electric, and we're going to push the boundaries when it comes to solar electric to see what we're capable of doing. No vegetable row is the same width wherever you go, so we had to design the system in a certain way where each wheel has its own drive module, so there's no shafts, no engine, so you can easily adjust the width of the row when you get to a new farm and work out it from there. And it was also omnidirectional, so you can actually come along and change it's easily for it to move around the headlands. So basically you drive this robot up and down the headland, and it tells you where the width of the paddock is, and you just let it go, and it will just go up and down the individual rows, and it's got a collection of sensors underneath, and those sensors are hyperspectral, infrared, and so forth, and they start to collect all the information about what's going on with the vegetables in that space. This robot ran for about 7 hours on batteries alone, and if you're in Queensland on a day like today, you get 24 hours out of it. So we're still pushing the boundaries and trying to get that full scope. But you can imagine that we're not far off from going 24/7, a robot on a farm, constantly doing crop surveillance. Okay, and that's really where it goes. They got excited by that process there, and they said, well, what does it mean to have an operational robot now if we wanted to go all the way through? And they gave us some more funding to actually build a more operational robot, and this one's called Ripper now, so Robot for Intelligent Perception Precision Application, but as in Ripper. Same concept. This one now operates for 24 hours, and I'll skip this one just out of the interest of time just to show you what's going on. The same process, a collection of sensors underneath, fusing information as the robot's going up and down. So this is on a lettuce farm in the Gippsland, down in Victoria. Here's the machine learning algorithms detecting individual lettuce in real time and also telling us the age of the lettuce. So whether it's 1.3 weeks old or 1.4 weeks old, which means whether one lettuce is underperforming compared to another lettuce next to it. We can then map out some distributions across it so we can get a yield estimate of what it looks like for that particular type of lettuce, and then we get proper yield estimates from there. Because if you want to do automated weeding, you can only do green on brown, but now because of the machine learning algorithms, we can detect where the plant is and where a weed is. And here we're not using any chemicals, it's just mechanically disrupting the weed and just going from there. And if you've got something going out there 24/7, then you're constantly mechanically disrupting the weeds. And here it's targeted spraying each individual plant. So if you wanted to spray fertilizer or chemicals on each individual plant, so a complete reduction of the chemical costs in that space. And also what we're looking at now is also soil sampling. So you're being able to kind of go to any plant and measure what's going. In this case, it's water conductivity, but eventually we want to be able to look at root structure as well. And this is kind of lessons that we're getting out of the mining industry. If you can build up information about what's going on in the soil as well as above it, you start to use the machine learning algorithms to look at correlations between what's going in the ground and above the ground. And you start to correlate variables between that and start to improve the productivity from there. The horticulture industry wanted to make sure that we were developing systems that catered across all of horticulture. So this is now using the same robot, but going back to the apple industry with it. Because if you can build the same modular robot across the whole industry, then you've reduced the cost. And what we're really hoping for is one day to not even have to pay for the robot cost. In fact, what you're paying for is just a collection of data, almost like you're leasing your iPhone and your iPad. And we can see that future coming along. But here it is going down the apple orchard, and what it's doing is it's detecting apples in real time. This white box that you see up here is the same white box that was looking down at the lettuce plants. It's now been reconfigured, and now it's detecting apples in real time. And what we can do is, you can see it here, it's that shooter system, and what it's doing is every apple that it sees is just firing away at the apples. again, as engineers, we just wanted to have a bit of fun and just see what we could do with it. The farmers, however, said, oh, this is great, because now if I can precisely detect where there's a pest, I'll just spray on that pest. I don't need to do blanket spraying anymore. Something about calcium as well, and being able to spray calcium in certain parts. And being able to do other things that we can do with this system now is look at tree architecture, and we're actually looking at solar radiation and how light penetrates through that tree. So for the first time, you can actually go to each individual tree and through optimization algorithms determine what is the optimal pruning that you need to do in order to maximize light penetration through the tree, and that becomes important. And this was some project funding that we got out of some philanthropic funding, and here it's doing the same thing as what I've shown you before, detecting individual plants, but it's on a very low cost robot. This robot here, we were trying to get down to the $5,000 to $10,000 mark. As much off-the-shelf componentry as possible. It uses a smartphone camera and also the smartphone as a computer, so we're not worried about comms here, and being able to detect individual plants using a smartphone and controlling the robot. And this is meant to be for all the mums and dads out there. So while the more expensive robots are going to be for the top 5-10% of the growers, what do you do about the other 90%? And the thing in the back of your mind, I think, is also important, is as you start to, these robots will start to talk to each other, because farmers will start to share information about what they learn. But what does that also mean about capturing biosecurity information, for example, and on a regional level? And how does that work? I'll quickly touch on the grazing livestock and some of the work that we're doing there. So the cattle industry was very interested in, can we build a robot that works on undulating terrain, very difficult long-range areas and so forth, and what does that mean? We were very interested in this because from my perspective it's all about animal welfare, and if you can have a robot for 24 hours, 7 days a week just hanging around the animals, collecting data about what's going on in the animals, but also collecting data about the pasture quality and so forth, pasture quality, good pasture, good animal, and so forth. And so we started to look at various things, like for example, can you herd animals? So in this particular study, we were trying to look at what happens when the robot gets closer to the animals, and how would you have to push them along if you had to push them along. And beef cattle, unlike dairy cattle, they're a lot more jumpy, right? So they move around a lot more in that space. So it made it a little bit harder for us. But the farmer doesn't think it's going to be an issue because he reckons the cows, well, at that time he thought the cows would get used to the robot, wouldn't be a problem, which is also a problem for us because this is a 100-kilo robot, 500-kilogram animal. You don't want them next to each other, right? So it's how do you measure and also keep a standoff distance at the same time. But then we thought, well, what if you had to move these animals to better pasture quality? How would you work in that space? And then we thought we'd try a bit of a Pied Piper technique, and that worked a lot better, right? So here the robot's got the hay at the back, and we drove the robot with the farmer, and the cows eventually got used to the robot, and then wherever the robot came out, the hay stack at the back there, and we could actually kind of just drag the cows along to the next paddock. The interesting thing was they were so used to the farmer's voice, so one of the next trials we have is we've got to put a couple of Boss speakers on the back of these things and just record the voice and go from there. But you can see what we're trying to do. We're trying to capture information in real time about each individual animal, where they're eating, how healthy are they, are we noticing any changes in any animal behaviour, does that mean anything about the health of the animal, and so forth. So that's really kind of the aspects there. It's quite interesting too because it talks a little bit about animal ethics as well. So if you are now able to operate a system for 24 hours, 7 days a week, is it more ethical to have a system next to the animals than it is to kind of leave them in roaming and what it might be? And it's one of those questions that also is on a bit of a debate. And this is just showing you some of the latest things that we're doing where we're looking at little probes to do some spraying, so detecting things like African boxthorn, so different types of weeds on these farms, being able to spray them, as well as being able to drill into the soil and capture the soil data so we can do, and what we're looking at is like a lab on a chip type of process. So can you actually build little microprocessor sensors that will fit on the robot that can measure soil properties and understand what the soil properties are in real time through the farm. Okay, so I did a bit of a lit study as well to kind of see where some of the trends are going. One of the big things at the moment now is non-chemical weeding, and looking at all the different types of technologies that might exist in that space: microwave, laser, steaming, flaming, mechanical weeding for different types of crops. So there's a wide range of techniques now that people around the world are starting to use, and that you can imagine that's a big thing for us as roboticists, because in many cases what you're doing is you're redoing the whole labour thing, but now you're automating that process. So the way we used to remove weeds, you're just doing that now, and you do that 24/7. So can we get to the point where we're not using any herbicide use whatsoever? And that was one of the things, despite and despite all the changes in weeds as they throughout the season. So that's one of the things that we're looking at. More importantly, if we're using solar electric, we're trying to figure out what is the right energy consumption here, and that becomes part of that intelligent system there, that looking at what type of weed, non-chemical weeding should I use given the amount of energy that I have available. We're also seeing a lot more of a discussion about how you would start to model the whole process from farming, biosecurity, etc., all into that, and the different types of techniques that are being available there. And some of the latest papers are talking about much more sophisticated statistical fusion process techniques and how they come through, and that's quite interesting. Similar to all that is this whole Internet of Things that you might be hearing about, and what does it mean about plug-and-playing sensors and technologies on farms, and how does that all fuse together. The one thing that I think is missing out of all that literature review, and I apologise for the big headings here, but this is the stuff that we've been able to pull out of the aerospace, defence, security and mining industry, is what's still missing is how do you fuse multi-levels, so spatial, spectral information, temporal information, how do you fuse all that together in order to build some large stochastic data fusion pipeline that you can then apply optimization techniques over. It's a lot of words there, but I hope you can kind of break it down. What I'm saying is that in the literature review that I've seen so far, it doesn't really tackle that, yet in other industries this is being tackled over and over again. So there's things in those other industries that you could learn from, that you could pull into this space, if what I'm seeing is true in terms of literature. So that's where I think it's all going, and just the discussions that I had with Lee when she was up at the ACFR, and kind of the things about maybe just some final thoughts that I wanted to leave with you in terms of my experiences so far with ag and biosecurity compared to other industries, and I think the things that you might want to look at and change as you're going through, which is all about how do you bring in this technology, right? And how do you design systems so that you can bring in this technology. I'll go back to that map that I showed you before. To me, this is probably key, is to sit down and understand what your information pipeline looks like, where you lack information, and I mean by statistical, not in terms of how much data you have, but statistically where you lack that information, where the uncertainty is the greatest, and from that being able to then cater for that process first, because there might be other automation tasks that you want to do, but if you can lift up the amount of information you have and be more statistically confident with that information, then that helps in the decision-making processes later. So I think going through that process, we've done this many times over in different industries, and it helps on capturing the return on investment, because if you can demonstrate that by adding in this robot, you're collecting more information, in the side, you're also doing a whole bunch of things. You're proving how you would use that type of system in that field. There's other things that you learn from it, but in the short term, you're getting that extra information, which is where the return on investment comes through. And that just makes it easier to kind of add the technology into the future. This is an agile process flow from Nordstrom in Sweden, and it kind of talks about the process that you kind of follow through in an agile manner. So what I found in agriculture, and maybe this is the same thing in biosecurity, you've got to sit down for about 6 months to 1 year, capture the requirements, then another 6 months to write the business case. Then we'll run a program for 3 years, and we'll just have some few milestones, and then we expect to see something at the end of 3 years. By the time you've done the business case, the technology's moved so far ahead. So it's how you change your business processes internally to accommodate for the fact that the agility's in there. This is almost like the research domain, and this is like the startup domain, and this is like the industry domain in this particular case. You can see that the whole idea is that there are these connection points that constantly cycle through, and you're constantly trying to develop your minimal viable product based on the research that's coming through, and the researchers have to learn about what's happening in that space in order to keep readjusting their hypothesis. So the whole thing transitions, and it's a game of figuring out what the different timescales are for these different things and how you fuse them together. I would slightly twist this by adding another circle down the bottom here, because what you find, especially with government departments and in the ag industry, there's still a lot of connection happening between that directly to the researchers. So there's another kind of little circular loop in here. But the important point to get out of this is to be a little bit more agile, or a lot more agile, depending on where you are, in terms of how you accept technology into that process. And usually what that means is don't worry about the technology, stand a level above that all, and think about the architecture and the platform that you want to have that allows you to just plug and play technology as it becomes available. You're not the only group that wants to be the best operators and not worry about the development of technology. Mining companies want to be the best mining operators. They don't want to build trucks. Aviation companies want to be the best operators. They don't want to build planes and so forth. And everyone's going through the same process again. So you can learn a lot from that industry. And the final thing that I wanted to mention was, it's a bit of a complicated slide, but what robotics is doing is, as you start, or sensors in general, automated sensors in general, is you're starting to get more and more knowledge about the world. What data fusion, machine learning techniques are allowing you to do is to say, how will that world grow as the future goes on? And I can build some sort of level of uncertainty about that and predict forward in that space. What's missing a lot is bringing the science community in with the data community and fusing those two things together, and that's where you get a lot of benefit out of it. But the important thing that I wanted to draw out of this was, where does the grower, the weed officer, the council operator, etc., fit into this whole process? And we're starting to see more and more, you've heard of probably Watson and IBM and whatever it might be, which is this fusion of structured and unstructured data. Structured data being data that you collect from sensors, and unstructured data being the gut feel that the farmer has about what's next. How do you bring those two pieces of it? Because they're important, because a robot can't do a lot of the strategic decision making that a farmer can do. It's just not capable of seeing that horizon or understand everything, such as the weather last year properly, or what the farmer next door experienced, or what the market supply chain looks like. Because all of these, so this translation of uncertainty here translates to economic uncertainty for the farmer. And you, as a robot, you're not allowed to make that decision about what you should do next. You want the farmer to make that decision because it's their livelihood that matters. And so it's how you fuse that unstructured and that structured data together, which I think is important. Again, you're not the only industry, government organisation that's looking at this. When you look at the mining or the aviation industry, they have years and years of paper recorded maintenance schedules, right? Now all the aircraft come in, all the trucks come in, and they have online predictive maintenance concepts that are happening in there in real time. But you still want to bring in that large data set into that. So how do you bring that unstructured written records in with that structured data is also the next thing that's coming through. And I think that's something to consider as well. So that's it. So thank you for your time. I hope that's given you some perspective. There's a historical drive there, but in terms of where the future is going as well. Again, I will iterate, there's so many other industries that are tackling in the same space, so you can learn a lot from those other industries, which I think is, which is important. And agility. The technology is not going to wait for you, and I think that's an important process if you're interested in how the technology comes through.